So it's been quite a long time since I made a video, but I wanted to make a quick video about wave equations because I feel like they get a bit of a weird rep within physics for looking quite ominous and complex. But here I'm going to show you how to derive the main kinds of wave equations with just a couple of key principles on the concept of operators within physics. So let's start with our general plane wave solution, which you may be familiar with. That's e to the I kx minus omega t. You can see that, right? Now, this can be rewritten equivalently as e to the I over h bar px minus et. Now, this follows because h bar over p equals k, which implies that p is equal to h bar times k, which we know already from physics. Also, it follows also that E over h bar is equal to omega, which we also know E is equal to omega times h bar, analogous to frequency times the normal Planck's constant. Of course, this is the reduced Planck's constant, or whatever you call it. Anyway, that's irrelevant. So what I'm going to do here is I am going to introduce you to the concept of operators. So let's differentiate this with respect to x first. So we'll call this the wave function 5x of t, and we're going to differentiate 5x of t with respect to this. So d phi dx gets us ip over h bar times our wave function, right, just from the rules of exponentials. Now, I'm going to just rearrange this for p, right? So times by h bar divided by I, remembering 1 over I is equal to minus I. And then we will end up with p of phi is equal to minus I h bar d phi dx. This is saying that momentum times this wave function is equal to this expression. Now, we can rewrite this in operator form by just removing here, rewriting this as p hat, removing here. And this is our momentum operator, therefore. Now, the same thing can be done with the equivalent process for time, differentiation with respect to time. So that's d phi dt is equal to minus I e h bar phi, leads us to e hat is equal to I h bar d, basically derivative with respect to time, right? So let's consider now, these are our fundamental things here that we need in this topic. Let's consider now conservation of energy, right? That's k plus v is equal to E. That should be quite straightforward, I suppose. Kinetic energy plus potential is equal to total energy. So obviously we know that kinetic energy, well, not obviously, some people may not know, that kinetic energy is 1/2 mv squared, but this can be equivalently written as p squared over 2m by just rearranging and rewriting. So let's make p squared over 2m plus v is equal to E here. We have that, right? And now we can rewrite this all in operator form from what we derived before. So this becomes p hat squared over 2m plus this potential operator v hat is equal to E hat, right? Now we haven't defined v hat, but we'll leave it as that. So now we're subbing in what we have minus h bar over 2m times the second derivative with respect to position plus v hat of phi is equal to minus, is equal to I h bar times the first derivative with respect to time. So you may be familiar with this. This is the Schrödinger wave equation, which is, like I've shown here, quite easily derived from just a couple of key principles. This is a notorious equation for being difficult to remember and also confusing looking, but as you can see, it can be derived from simply, this plane wave equation. So that's the Schrödinger wave equation, which isn't exactly what I wanted here to show you, but it's a good introduction. What I wanted to show you was, I'm going to leave this up here because we're going to use this, is relativistic wave equations. So consider e squared is equal to p squared c squared plus m squared c to the 4, which you'll learn in first year special relativity if you haven't already. We can of course rewrite this as well in operator notation. So let's consider minus h bar squared d squared phi dt squared is equal to minus h bar d squared phi dx squared c squared plus m squared c to the 4. Now this is just this, but written with the operators. And let's divide through by c squared and h bar, sorry, that should be squared, and h bar squared, right? So that leaves us with minus second derivative of phi with respect to position squared is equal to d squared phi with respect to position squared plus m squared c squared over h bar squared, sorry, minus, right? And then typically, oh sorry, my apologies, there should be a 1 over c squared here, minus 1 over c squared. And then typically we could, well, we could leave it like that, or we could rearrange to make one side equal to 0 and have everything on the other side. But for now I'm just going to leave it like this, right? This is a relativistic wave equation, which again, relatively easy to derive, pun intended. And it does look complicated, yes. But I thought that it might be interesting to compare this with classical physics. How may one associate this with the non-relativistic, or even really non-weird physics-y stuff anyway? So let's consider a wave. Sorry for the weird cut there. Someone was being a little bit loud and distracted me for a second. But yeah, considering waves and even mathematics beyond just physics, we may be familiar with the wave equation, but again, it's sometimes seen as a bit mysterious or whatever. So I'm going to show you from this how we can get that classical wave equation, which you may have noticed a minute ago with the relativistic form. So we have E equals pc for a massless particle. If we square both sides, you have E squared, P squared, C squared, we can apply our operator minus H bar D squared D T squared is equal to C squared, or should I say minus C squared H bar squared second order position derivative. Then we can divide through by minus C squared H bar squared, which leaves us with D squared, or I can apply the phi operator here. We can operate it upon a wave function phi. And then we have dt squared is equal to 1 over c squared is equal to d squared phi over dx squared. And that's our regular wave equation from this quantum mechanical concept, quantum mechanical proposition. Now, I believe this has a name when you don't operate it on something, the 1 over c squared time derivative and position derivative. I think that's the D'Alembert operator, which probably comes from this, but I don't actually know that, so I won't comment on it. But yeah, it's been a while since I made a video, so I thought I would just come back briefly to talk about this. And hopefully there'll be something else I could talk about later as well. But yeah.